Good. So then the first topic in the new year to prepare ourselves for the random field theory based inference in fMRI is statistical testing, where we will be interested in both the single test scenario, where you basically do one test. So that would be evaluating the t-value scenario of a single voxel, and the multiple testing scenario, which of course then refers to doing many tests at the same time. And we will address statistical testing in a kind of general language, and the reason for that is that in fMRI, at what we've seen in the SPM table, we have what is called peak level, cluster level, and set level. And peak level, or also called voxel level, that's roughly equivalent to doing a t-test, and then doing a t-test in a multiple testing scenario. So in principle, we could just also talk about t-tests and not give a more general language if we only want to talk about peak level or voxel level inference. But most people in fMRI do cluster level inference, which refers to cluster size or volume tests. So the question is a cluster of a specific is a cluster of a size that large that it's unlikely to occur by chance, and because this then is of course different from a t-test. The statistic that is being used is not the t-statistic but a cluster size statistic. We need some language to frame also such tests, and this is why we use this general language to introduce statistical testing. The same actually applies to set level, where it's the cluster number test actually, so how many clusters there are. And again, this has a test statistic which is not the t-statistic, which then has its own distribution under the null hypothesis and so on. So we need a language that is more general than the language that we know from one simple t-test from undergraduate statistics. So that's the motivation for using such a general casting of statistical testing. So be a little bit patient. In the end, we will always come back, of course, to a t-test and immediately say how the things that we've now introduced apply in a t-test, but then we have the language for later to apply them also to cluster size tests or set level or cluster number of cluster tests. And it's also very important to have a general language to introduce things like the family-wise error rate and how the maximum statistic can control the family-wise error rate. All of this is much more readily addressed in a general language. So that's why we introduced that. So we start with the single test scenario. And as I already mentioned, you have access, of course, to the script in this Google Drive folder, and I now took out some stuff that we haven't discussed yet from the script, and update a little bit as we go along. So definitely check before the session that is happening here the latest version of the script, then we are on the same page, because I'm trying to tailor it best so that it works best for what we're doing this year. So what I'm now doing is the section 14 in the script for this year, that is statistical testing. And there are a number of things to discuss. So as an overview, we first need to understand what test hypotheses are. then what tests are, test error probabilities, all in a single test scenario. Significance levels, p-values, and p-value based tests, and how tests are typically constructed. And this is what we would do in the single test scenario, what we've done in the single test scenario, where we mostly, I guess, familiar, or at least just a simple generalization from what you know about t-tests. Then we go to the multiple testing scenario and cover the same aspects, but we'll also emphasize the differences then. Yeah, I think that's enough of prelude, so let's just get started. So what we will always base everything on is that we assume that there is a probabilistic model. And of course the probabilistic model that we mainly have in our minds now is the GLM. I'm doing it here even more general. Doesn't hurt, because we will not discuss this probabilistic model much, and once we discuss it, then it will usually be the general linear model. So I'm just saying there is some data, for example the voxel time series of a single voxel of a single participant. There are some parameters theta, and of course there's a probability distribution over the data that depends on the parameters. And and the data usually will take on values in n dimensional space. So again, for example, the 400 data points from a single voxel time series. And the parameter is part of or is an element in a parameter space. So parameters can of course be, for example, the beta values. And I think it's easiest in the beginning if you think mostly of a single beta value for a single regressor, for which you then want to test things of whether this beta is different from 0. I think that's easiest, and you can of course always generalize this to contrast, and you want to know about their differences and then reformulate things like that, but you can also just think in terms of a single beta parameter. Now, once this is set up, and of course we've set this up to some degree by discussing the GLM, we can define test hypotheses, which are statements about the value of the true but unknown parameters in relation to a partition of the parameter space. So let me say that again, hypothesis. So in a test scenario, what you do is you take the parameter space, theta, and you partition it into two components, so two subsets, big theta 1 and big theta 2, such that so you do a partition, which means you take two subsets which together give you the parameter space, and these two subsets are non-overlapping, so the intersection is the empty set. And then you make two statements. The true but unknown parameter is in one of these parts of the partitions, so the true but unknown parameter theta is in the partition big theta 0, and you call this null hypothesis. So sometimes this is then also written like this, and we call this null hypothesis. And then you do the other statement that the the parameter is in the other part of the parameter space, in the other subset, and this is the alternative hypothesis. So to readily associate with something, so for example, if you do a one sample t-test, of course your data is so just remember the one sample t-test design in a GLM. You have your GLM, and your design matrix is a column of ones, so that's just ones, and your beta is the expectation parameter for each of these data points, and this beta in undergraduate statistics is then the population expectation or the population parameter, and then often also referred to as mu, for example, so as the expectation of the population where the data is sampled from. Of course, there is no population, and I don't also like this population metaphor that much, because populations always sound as if they are finite size, but this is of course of infinite size, or the real numbers from which you can sample from. So in this scenario, you can of course have the null hypothesis that mu is 0. This is how you usually refer to it. Mu is 0 or mu is not 0. In this language of, in terms of the partitions, this would mean that theta is an element of the null hypothesis. Or we can do it like this, theta. Or, so that's the null hypothesis, or theta is an element of parameter space without the null, which is the same thing as saying that the expectation parameter is 0 or it's not 0. Of course, you can also specify things like larger than 0 and things like that in terms of these parameter space partitions. If one of these partitions, so one of these subsets of parameter space, only contains a single parameter, that is called a simple hypothesis. So if there's only a single parameter in this subset, and if only the null is in this hypothesis, then it's also sometimes referred to as nil hypothesis. Of course, you can also test simple hypotheses which are not nil hypotheses, things like mu equals 2 or mu equals not 2. You can also frame in terms of these partitions of parameter set. So the important thing is that alternative and null hypothesis and alternative hypothesis are statements about parameter values. That's the most important thing to take from that. And then we can talk about the distribution of the data under the null hypothesis, which we would then, for example, write like this, or the distribution of the data under the alternative hypothesis. And you can have a philosophical argument what you want to call null hypothesis and alternative hypothesis. So in general, the way it's done in the literature is that both the statement that the true but unknown parameter is a subset of theta 0 is called null hypothesis, but then, oops, why do I have this down? But then also the subset itself here, so this theta 0 is called null hypothesis, because it's just a little bit redundant to always say theta in theta 0. You might also just say theta 0 is the null hypothesis, so it's a set, it's a parameter, it's a subset of parameter space, and that's called the null hypothesis, and theta 1 is a subset of parameter space, which is called the alternative hypothesis. And so you might know that there are two ways about statistical testing, which are kind of the Fisher and the non-person approaches. Fisher's approach was more to always just talk about a null hypothesis and not specify an alternative hypothesis. And then Nyman Persson later on introduced alternative hypothesis. So in our scenario, we will always have the null hypothesis and the alternative hypothesis. The main reason for that is that you cannot have discussions about power if you don't introduce alternative hypothesis. And power in fMRI is an important thing. We will not discuss that here because that would be would go far too far. But if you want to have a concept like power, then you need alternative hypothesis. So we will always have this binary statement of, or this binary world of a null hypothesis and an alternative hypothesis. So simple and composite. Yeah, if you have more than one element in a hypothesis, this is also called composite hypothesis. So yeah, I think this is the first thing. So this is now the, so basically a probabilistic model together with test hypothesis, so a partition of parameter space into a null hypothesis and alternative hypothesis. This sets up the background for a test scenario, but it's not a test yet. It's just we have a probabilistic model and we have our parameter subspaces. And of course, we now want to somehow, based on observed data, somehow make a statement what we think about the parameter with respect to the null and alternative hypothesis. And we also want to ensure that if the parameter is really part of the null hypothesis or the alternative hypothesis, that we mainly do good decisions in terms of our tests, and this is now what the remainder will discuss. From my perspective of inference, hypothesis testing of course throws away quite some information. So usually when you do parameter estimation, you try to find a value that you think is roughly the true but unknown value, or for example in Bayesian inference you try to give an uncertainty statement about the value of the parameter, that it's in a certain interval with high probability. In hypothesis testing, what you essentially only say is that the parameter value is in the null hypothesis or in the alternative hypothesis, and this of course is quite coarse related to the parameter space. So if you say in the end of your analysis, well, the parameter is likely not zero, that is of course far less informative than saying the parameter is with like 80% probability it's in the interval between 0.8 and 1.2. Of course there's more information than saying it's not zero. So in this sense, hypothesis testing is kind of a coarse parameter inference. But that's more side note. So this is the hypothesis, the probabilistic model and the hypothesis, and now let's come to a test. So a test is a mapping from the data space to the set 0, 1. So a test, which I will denote by phi, takes a data point, so an n-dimensional data points, so for example our 400 time points of a single participant, single run, single voxel data, and maps it into the set 0, 1. So it takes our y and maps it into phi y. Now one can have long discussions of how to write this. So in the script I write it like this. So our test is written like this, and takes a data point and maps this onto this thing. So what do I mean by this? What I try to emphasize here is that this is the data, and the data is a random variable. Yeah? So we can sample data, and if we sample data again and again, we get different data out. That means the test as a function of the data is also random. Yeah, so if we sample data again, the test, depending on how we specify it, will come out with something different. And however, I don't want to, and this is why I use this somewhat strange notation for the test here, I don't want to define a test on the space of random variables, because then we have a function defined on functions, and this all gets a little bit complex. So I define it on the data, meaning that if we have 400 data points, our test is a function that takes these 400 data points and gives us back a number 0 or 1. And to nevertheless emphasize that this is a random entity, I carry with it this this big data variable. You could also write a test like this. So just do things like this. Y maps to phi y. But this would mean you take a data point and get out a number 0, 1 deterministically, because a test is a function, it's deterministic thing. And then the whole notion of randomness is not in there anymore. So this is why in these notes I then later on write tests like this. So phi on a data random variable takes on a value for a specific data point. You can ignore it, and you can cross out all of this big Y if you don't like it, but don't forget that tests operates on random variables, and hence the outcomes of tests are random, and we will, and of course we have to talk about the probabilities of test outcomes, namely test error probabilities, type 1 error, type 2 error, and there it's important that we keep in mind that the values that tests take on are realizations of random variables. Hence this somewhat a little bit annoying notation, which I then simplify into this. But yeah, like I said, you can, if you don't like it, get rid of this, but keep in mind that this whole thing is random as a function of the random variable data. But it's also deterministic once you have a realization of the data. That's the tricky thing about tests. Now, of course, the question is, what are these values? So if phi y for a specific data realization is 0, this is supposed to represent the act of not reject null hypothesis, which in the Nyman-Pearson framework is the same as accept null hypothesis, although some people don't like this, but that's just philosophical debate. So don't reject the null hypothesis, accept the null hypothesis, which is also the same as reject alternative. And I think that's everything. Reject alternative. So the easiest, I think, is to remember that if the test delivers the outcome 0, this refers to accepting the null hypothesis. Because it's 0, it's accept the null hypothesis. Then the test, of course, can have another outcome, because it's mapping to the set 0, 1. And this is reject null hypothesis. Or, of course, easiest is to accept alternative. Or not reject alternative, but I think that's overkill. Accept alternative. And that's, I think, the easiest to think about. So the test is a function of the data. So think again, you have 400 data points, then you do a test, and this test is just a function, and it looks at the data and then gives you back a 0, which means don't reject the null hypothesis or accept the null hypothesis, or it gives you back a 1, and that means reject the null hypothesis or accept the alternative hypothesis. So I think it's easiest, and I try to use this language because this maps easiest to 0 and 1. So accept null hypothesis, test says 0, accept alternative, test says 1. So of course, when you do a t-test, this is kind of the overall, so if you think about a t-test, of course, this is the overarching thing that is happening, right? So for a t-test, you first have some data, then you compute things, you compute a sample mean, sample variance, compute a t-statistic, then you have your t-statistic compared to the critical value for a given significance level, and then in the end, you say it's significant. So this would mean accept the alternative hypothesis, reject the null hypothesis, or you say it's not significant. That would mean you don't reject the null hypothesis. So you reject the alternative. So what this specified so far, so this test was this entire procedure. Yeah. Now, of course, the test that we mainly will be dealing with, I have to stop in a second, take a specific form, namely they are given as the composition of a test statistic and a decision rule. Now a test statistic, for example the t-statistic, is a mapping from the data space to the real numbers. This can also be our cluster size statistic, where actually the data that we're looking at is the entire data set. So first we transform the data into a single number, so that's what's happening here. And then we apply a decision rule, which is applied to our test statistic and yields a value in 0, 1. So this would be in a t-test if you have evaluated your t-statistic and then you compare it to a critical value that you looked up in some table, and then you say, okay, I want to reject the null hypothesis and declare significance, or I don't want to reject the null hypothesis and declare not significance. So not significant. So this is the decision rule. Good. I think I have to stop here because I have to start with the other lecture. We discussed some of these test theoretic concepts also in statistics for data science, so there are some videos already if you want to watch that. Otherwise, I will continue with the construction of the test here next week. Sorry, we have to stop, but time is running out. Yeah, so I think so far there was not much to ask. So the thing is, try to be happy with that a test hypothesis is a partitioning of the parameter space, and that a test hypothesis means that you say that the true but unknown parameter is part of one of these hypotheses, and then that a test is this general mapping from data to 0 and 1. And then the interesting stuff based on this, namely test error probabilities and significance levels, will come next week. All right, see you